All right, this is my first set of notes from Chapter 2, phase diagrams of pure fluids. And specifically in this first set of notes, we'll just look at reading phase diagrams of pure fluids. Okay, so this is our first set of notes from Chapter 2. Okay, and to kind of motivate things in terms of where we're going, is on the first slide we're going to talk about the Gibbs phase rule. And so the Gibbs phase rule tells us for number of components and number of phases present in your system, how many degrees of freedom you have. Okay, and so what that means is, if you think back to your Thermo 1 class, if I had to go to my steam tables and look up properties for supercritical water, okay, I needed to specify two intensive variables. If I knew, say, temperature and pressure of my superheated steam, that was sufficient to go to my steam tables and look up all of the thermodynamic quantities of interest. So in general, if I have a single component, single phase system, I have 2 degrees of freedom. And so what that suggests to me is that all of my thermodynamic quantities must be related to each other. So if I know pressure and temperature, and that's enough to go and look up enthalpy and entropy, somehow enthalpy and entropy must be related to pressure and temperature, right? So all of our thermodynamic quantities are related to each other. And in Chapter 5, we're going to work out those relationships. In this chapter, we're going to focus on the PVT phase behavior of a fluid. Why pressure, volume, and temperature? And let me pause and say, when I talk about PVT behavior, when I say V, I'm talking about molar volume. Okay, it's molar volume, which is an intensive quantity. Okay, so we focus on PVT behavior because if all of my thermodynamic quantities are related to each other, well, PV and T are going to be my favorite because they're physical properties that I know and understand, and I can readily measure them in the laboratory. Okay, a couple other motivating factors for this chapter is in Chapter 7, we're going to talk about the theory of VLE. And so here we'll look at how to read PVT phase diagrams, so that when we talk about the theory of VLE and predicting phase diagrams and things of that nature, we have an idea of what the results should look like. And then, having a good idea of phase behavior of pure component systems is a good idea before we look at phase behavior of mixtures. Okay, so I mentioned on the first slide we're going to talk about Gibbs phase rule. Well, here it is in all its glory. Okay, so in the text we introduce Gibbs phase rule much later, but I think it's important to introduce it here very early on, and then to keep that in mind as we work through the material. So the Gibbs phase rule in all its glory is F equals n minus pi plus 2. So the number of degrees of freedom, or the number of independent intensive properties that must be specified to fix unambiguously the thermodynamic state of my system, is equal to n, the number of components, minus pi, the number of phases, plus 2. So again, if I have a single component, single phase system, I have two independent variables. I have two independent variables that need to be specified to fix the state of my system. If I have a single component system at two-phase coexistence, so say I'm looking at my saturated steam tables, I have water and two-phase coexistence, that n minus pi is -1, so that plus 2 tells me that I have just 1 degree of freedom. So water at two-phase coexistence, if I just know the temperature and the fact that my system's at two-phase coexistence, that's enough to specify the thermodynamic state of my system. Okay, so we said we're going to focus on PVT behavior, and again, Gibbs phase rule tell us for a single component, single phase system, I have two intensive variables. Okay, and what that means is once I specify, say, pressure and temperature, all of my other thermodynamic properties are fixed. So somehow all of my thermodynamic quantities must be related to each other. So in Chapter 5, we'll work out these relationships, and our focus here is understanding PVT behavior, because if all of my thermodynamic quantities are related, the three favorite ones to work with are going to be pressure, volume, and temperature. They're all physical properties, and they're all properties I can readily measure, and I know what the heck they are. Okay, and so that's what's reminded here in the notes. Okay, and then the other thing I mentioned here is that we're not going to look at three-dimensional surfaces like we have here. Typically, we look at two-dimensional surfaces. One, because they're easier to draw, so it's easier from a convenience standpoint. But the other thing is, if I think about the limiting case of a single phase system, I have 2 degrees of freedom. Okay, and so if we specify 1 degree freedom, I can plot a independent variable versus a dependent variable, right? Or a dependent versus an independent variable. Okay, so it becomes easier to plot from a convenience standpoint and easier just to work with. Okay, all right. So we're going to start by looking at our pressure volume surface. And so when we talk about 2-dimensional phase diagrams, we're just going to be looking at different 2-dimensional surfaces of our phase diagram. Okay, and so before we look at our PV surface, what I want to mention is when we have 2 phases of coexistence, we have mechanical equilibrium, thermal equilibrium, and chemical equilibrium. The 2 we're going to focus on right now are mechanical and thermal. Chemical is something we'll look at and talk about later on. Okay, but mechanical and thermal you should have seen already. Okay, deviations from mechanical equilibrium is fluid mechanics. Deviations from thermal equilibrium is heat transfer. So mechanical equilibrium, if I have 2 phases in coexistence, they're at the same pressure. Okay, and so what that means is if I have 2 phases at mechanical equilibrium and they have the same pressure, equality of pressure just means that there's no driving force for PV boundary work between the 2 phases. If I have 2 systems at thermal equilibrium, okay, or 2 phases at thermal equilibrium, we have an equality of temperatures between those 2 phases. And so what that tells us then is there's no driving force for the exchange of heat between the 2 phases. Okay, cool. Chemical equilibrium you might not have seen before, but essentially that's a topic of a mass transfer class. And so that tells us that we have an equality of chemical potentials of our 2 phases of coexistence, so there's no driving force for mass transfer between the 2 phases. Okay, but the first plane we're going to look at is this PV graph. Okay, and so we have plotted here pressure versus volume. Okay, and so this dome here, okay, is going to correspond to our coexistence curve. If I'm underneath the dome, I have a 2-phase system. If I'm outside of the dome, I have a single phase. Okay, cool. These lines drawn here are lines of constant temperature. They're called isotherms. They go from low temperatures at T1 to high temperature at T4. Okay, cool. So low temperatures to high. We said that if I'm underneath the dome, I have a system at 2-phase coexistence. If I am to the left of the dome, okay, as labeled here, we call it a subcooled liquid or a compressed liquid. So what does that mean? Okay, well, if I'm at this point here, this point L, so that's on my coexistence curve, I have a system at 2-phase coexistence. Okay, so if I jump from isotherm 2, which this sits on, to isotherm 1, well, isotherm 1 is at a lower temperature, and if I jump over to isotherm 1 at the same pressure, okay, that takes me off of my saturation curve, and since I decrease the temperature to get myself in that single phase liquid region, we call it a subcooled liquid. Okay. Likewise, if I'm to the right of the dome, I have a single phase. I have a single phase vapor. Okay, and as labeled here, we often call it a superheated vapor. So how it gets the name superheated is if I'm at this point V on my dome. Okay, so if I'm at point V on my dome, and that would put me on this isotherm given by T2. Okay, so our isotherms, when they cross our phase envelope, are flat. Okay, why? Because when I have a two systems at coexistence, we have equality of temperatures and pressures, right? So these 2 points are at the same pressure and they're at the same temperature. They're on the same isotherm. Okay, but if I'm at point V, which corresponds to isotherm T2, and if I keep pressure constant and I were to jump over to this isotherm's at Tc, my critical temperature, okay, but that's at a higher temperature at the same pressure. So in order to get to that vapor region, keeping pressure constant, I need to increase the temperature, and that's why I call it superheated. Okay, cool. Okay, so these are our isotherms. Okay, so they're steepest at low temperatures. And so what this means is when I'm at low temperatures, if I look at this isotherm and I think of it as, the slope of this is dp dv at constant t, or the inverse would be dv dp at constant t. Well, if I think about liquids at low temperatures, they're fairly incompressible, right? So if I have water at 0 degrees C, as I apply lots of pressure to it, the volume's not going to change much, right? And so, we see that by looking at this isotherm where dv dp at constant t is essentially 0, right? Or the slope is infinite. As we increase the temperature, the slope begins to deviate from this limit, and as we get to the critical point, it's squishy, and as we get to supercritical fluid, it's definitely compressible and squishy. Okay, cool. Okay, so this is our phase envelope. Okay, and so if I'm at point D, so if I specify pressure and molar volume in my system, and it puts me under this phase envelope in a two-phase region, we're going to get phase splitting. Why are we going to get phase splitting? Well, Gibbs' phase rule tells us that if we have a single component two-phase system, I only have 1 degree of freedom. So I can't specify pressure and volume because then my system would be overspecified. I can only specify one, pressure, right? Pressure or volume. Okay. And so in this case, though, if I specified P and V that put me at D, I'm going to get phase splitting along an isobar, right? I get phase splitting along an isobar and isotherm, because my two phases at coexistence are going to be at the same temperature and pressure. Okay, so if I specify a system, so maybe I have a closed system, and I specify the pressure and volume of that system. Okay, that's fine. Okay, that'd be the total volume. Okay, but within your box, your system's going to split to form two phases: a liquid phase and a vapor phase that are in coexistence with each other. Right, and how I find or identify those two phases on my phase diagram is I just read across on my isotherm and isobar to where I hit the edge of my dome. Right? Cool. All right. So why that happens, Gibbs' phase rule tells us it happens. Okay. So now if we look at our isotherms, okay, so we said low temperatures to high. Okay. So as my temperature increases, okay, we get to the point where we reach this special isotherm, which is called my critical isotherm. Okay. Cool. Okay, so we'll get back to this in a second. So if I look at my dome, right, my phase envelope, okay, it's widest at the bottom at low pressures. And then as my pressure increases, as I approach, where my critical isotherm hits my phase envelope, okay, where I get to the, top of this dome corresponding to my critical point, okay, the two regions of my phase envelope get closer and closer to each other. So what happens is as I move up in pressures, okay, until I get to this critical point, okay, at my critical point, my two phases no longer exist and become just a single phase. So at the top of this dome, that corresponds to my critical point. It's where I no longer have two-phase coexistence, where my two phases become one. Okay, so my isotherm goes through an inflection point at this point. Okay, and in terms of my dome, right, my liquid and vapor arms of my dome become a single point. And so if I'm at pressures and temperatures above this critical point, what happens is that means we can only have a single phase. Beyond the critical point, two-phase coexistence is no longer possible. Okay, and so what's indicated up here is, this is my pressure axis. So this would be the pressure at my isotherm, or the pressure at my critical point. These are my isotherms. So this one corresponds to my critical isotherm. So above my critical pressure and above my critical temperature, we're in this supercritical fluid region. Okay, and so it's a single phase region, and we typically call it supercritical because at this point, calling it a liquid or vapor really doesn't make sense. It's only down here it kind of makes sense because it's possible to have two distinct phases. Okay, so up here I have supercritical fluid. And so a special point about my critical isotherm again at this critical point is it exhibits an inflection point. So one, if I look at my critical isotherm, its first derivative is 0 here, and then its second derivative is also 0. It goes from being concave up to concave down. Okay, and we'll use that later on when we talk about cubic equations of state. Okay, So the last thing we'll point out with our PV surface, okay, so if I look at an isotherm, okay, so these isotherms are lines of constant temperature. So if I'm on an isotherm in the limit that my pressure goes to 0, so remember this is low pressures to high, so the limit that my pressure goes to 0 or my volume goes infinity, which would push me way out to the right, we're going to approach ideal gas behavior. So if I just think about the limit that V goes to infinity, if I have a closed system and my volume's going to infinity at constant temperature, what's going to happen is the distance between those molecules within my system is going to go to infinity. And if I think back to my LJ potential, if the distance between my molecules goes to infinity, they're essentially no longer going to see each other. They're not going to interact, and that's going to give us the limit of a non-interacting state, an ideal gas state, okay, or an ideal gas limit. Okay, so that's our PV graph. The next one we'll look at is a PT plane. Okay, so you look at pressure versus temperature, pressure versus temperature, and here we'll just look at our vapor-liquid region. Okay, and so it starts at our triple point where we have solid, liquid, and vapor and all in coexistence, and it goes up to our critical point. Okay, so what's different about this PT plane, okay, is if I go back to PV. So PV, we said when we have two phases in coexistence, they have the same temperature and pressure. Okay, and so when I have a PV plane, I have a dome that corresponds to my two-phase region. Why I have a dome is at coexistence, my phases have the same temperature and pressure, but the molar volumes are different. Okay, and so when I have a given specified pressure volume that puts me under the dome, okay, I get phase splitting along an isotherm and isobar because those phases will have the same temperature and pressure, and then I'm going to get two unique molar volumes. When it comes to my PT plane, I don't have a dome, I just have a line. Okay, and why I just have a line designating my two-phase region or my coexistence curve is because at two-phase coexistence, I have equality of temperatures and pressures. So my liquid that's in equilibrium with the vapor are both going to be at the same temperature and pressure. So my coexistence points, or my phase boundary is just a line in this case. Okay, so now I have P versus V, and so what I've plotted is these dashed lines. These are going to be called isocores. Okay, so why do we call these isocores? Well, so if you look at this point that's labeled, if I'm at point V on my coexistence curve, this would correspond to a point at two-phase coexistence along, say, this isocore. Okay, and so if I wanted to bring myself over to the liquid region over here, what that corresponds to is if I increase the pressure, or if I hold on, I'm having having a moment here. So this is my PT plane. Okay, so if I'm at this point at a given temperature and pressure, I could do one of two things. Okay, so this region to the left is going to be our liquid phase. To the right is going to be our vapor phase. So what happens is at fixed pressure and temperature, okay, if I just think about a system at two-phase coexistence, is if I were to decrease the pressure, okay, so if I decrease the pressure, so if I have, say, a piston cylinder, and inside that piston cylinder I have two-phase coexistence, and now I pull up on the piston to decrease the pressure of my system, okay, so if I'm here and I decrease the pressure, what that's going to do is it's going to push me towards vapor region, okay, or equivalently, if I think about my piston cylinder and I increase the pressure on my system, okay, that's going to correspond to, if I'm keeping temperature the same, say, if it's in a bath, moving up here, it's going to push me towards a liquid region, okay. So when I look at this phase boundary, okay, you can think about thought exercises like that. Liquid's going to be over here, vapor is going to be over here. Okay, you could also think about it as keeping pressure the same, but increasing or decreasing temperature. Okay, so if I'm at this point on my two-phase coexistence, and if I keep pressure the same, but I were to decrease the temperature, cool it down at constant pressure, it's going to push me over here towards the liquid region. If I think about a system at two-phase coexistence, I keep pressure the same, so maybe I have water open to the atmosphere, and I increase the temperature, that's going to push me to the vapor region. Okay, so here it's labeled compressed liquid and superheated. So where the compressed comes from is if I'm at a constant temperature in my two-phase coexistence boundary, and I want to go to the liquid region. Okay, one way to do that is at constant temperature, increase the pressure. So if I increase the pressure, right, that's pushing me up towards this region. It's compressing my fluid. I get a liquid. In terms of superheated, another way to think of it is if I keep pressure constant again and I increase temperature, right, I heat up my fluid even more until I get to that single phase vapor region. Okay, cool. So that's my phase boundary. These are iso cores. Okay, these are going to be, again, this is lower temperature. Well, lower temperature, this is more vertical. The molar volume changes less at constant at a given temperature. If I were to look up, from the last graph, dVdP at constant T. So if I were to keep temperature constant, molar volume is not going to change much. Okay, so my phase boundary, it's going to terminate at my critical point. So above my critical pressure, my critical temperature, I have a single phase called the supercritical fluid. Okay, cool. So this is PT, phase boundary. A common way to represent this is we'll derive a Clapeyron equation in Chapter 7. This is curved, so this is essentially exponential. And so, one way to plot a PT plane is in the Clapeyron style, log P versus inverse T, and that'll linearize your graph. But we'll talk about that later. The very last graph we want to look at before we wrap things up is a ZP graph. So Z being my compressibility. So compressibility is defined as PV over RT. So Z is also intensive. So again, remember V here is intensive molar volume. Okay, so you probably saw Z before in your, I don't know what you call equation of state for real gases. So my compressibility is defined as PV over RT. We're in the limit, so we said in the limit that P goes to 0 or V goes to infinity, I have an ideal gas. So in this case, in the limit that I have an ideal gas, Z is equal to 1, right? Because this is just PV equals RT is my ideal gas equation of state. And so I can plot, Z versus P. And so before in the first slide we had P versus V. So it's just essentially a dome flipped, right? And why it's a dome flipped, Z is directly proportional to V, and so Z is not going to be equal to my two phases at coexistence. So here's Z plotted against P. I have a dome for two-phase coexistence. Okay, the top of my dome, right? We're going to terminate at my critical point, and so here I have isotherms plotted again, right? And so we don't have quite as many, right? So T1's a little harder to see. I'm going to go from low temperature all the way up to high. Here's my critical point, vapor region, liquid region, and then I'd be supercritical up here. And this is going to be our, kind of our stepping point for the next set of slides once we start to talk about corresponding states theory and cubic equations of state in terms of getting data collapse on a ZP graph such as this. So with that, we'll wrap up this set of notes and we'll move on